Okay, so in this video we're going to be looking at kinetic energy this time. So we've talked about potential energy, we've talked about the different types of energy in general, but today we're going to be looking at specifically kinetic energy. So, kinetic energy, N-E-R-G-Y, that is our focus. But before we can talk about kinetic energy, we got to go back to the others. So the first thing that we're going to talk about when we talk about kinetic energy is just what are the types of energy that we know exist. We know that there is kinetic energy, obviously. All right, and we know that with kinetic energy that it requires movement. That's the big thing with kinetic energy. We need movement. The other type of kinetic energy that we have is we have thermal. So we have thermal energy. Now with thermal energy, this energy is that unique stuff. That's the stuff that whenever we lose energy. So this is lost energy. And then our final type of energy that we deal with, we know, is the stored energy, is the potential energy. Now with potential energy, I've heard some say that potential energy is when it's not moving. Now this isn't true. Okay, it can't be just that it's not moving, because potential energy is stored energy. Now, technically, an object could have potential energy and be moving. So if you take a ball that's up in the air that's falling down, well, that object is moving, but because it's up in the air, it still has potential energy. So we have to be careful when we say that moving, not moving, things like that. The only one that matters is movement. Same, you take this same object and we put it on the ground. That's a horrible ground. We put it on the ground, and it's sitting here, sitting on the ground. Well, now it's not moving, but because it's sitting on the ground, it has no potential energy. So it's not that it's not moving. It has to have energy stored, either through the two types. So we have two types of potential energy that we know of. We know that there's elastic, and we know that elastic energy is the energy with springs. And then we have the other type, which is called gravitational. Sorry, I had to spell that out. Now with gravitational, we can see it right there. We know that that involves gravity. Now, if we have gravity with our gravitational energy, potential energy, well, we kind of have to ask, when is an object going to have more gravitational potential energy? So let's continue and let's look at what gravitational energy, potential energy is. So let's go back to the ball. So we have the ball that's up in the air, okay? And let's put the ground down here somewhere. So this object is up in the air. Well, let's take a second ball and let's put it at the exact same height. Now, these two balls, aside from the color, these two are identical, we'll say. So which one has a greater gravitational potential energy, or GPE? Okay, so which one has a greater GPE? Well, neither of them. They're both at the same height, and they're both identical. So there's nothing that's, it's going to be just as hard to lift this black ball this high as it is going to be to lift this blue one. They're going to be as difficult to lift. You're lifting them just as high. So both of them have the exact same amount of gravitational potential energy. They're going to be able to move just as far. They're going to hit with just as much force. So both of these have the exact same amount of energy. Same thing if I were to take these two objects and I were to put them down here on the ground. Both of them have the exact same gravitational potential energy. But let's take another scenario. Let's take that object and let's say it's a little bit lower. Let's say it's right here. What would I have to do to give the blue object, the other ball, a higher potential energy than the black one? Well, put it higher. So now it took more work to travel this farther distance than it did this shorter distance. So that means this object here has a greater GPE. Okay. We can take this farther as well. Let's go back to, let's have another surface here. And let's say we have two objects. Let's say we have, wrong color. We have our regular ball again. Let's switch it. Let's go to a purple one. And let's say this purple one, for the sake of argument, let's say this is a bowling ball. Now, which one is going to have more gravitational potential energy? Well, they're both lifted up about the same height. But think about it, if you were to lift both of these up, if this was, say, a tennis ball and this was a bowling ball, which one is going to be a lot harder to lift up this total distance right here? Well, this one right here, the bowling ball is going to be a lot harder to lift up. It's going to take more force to travel that distance, or in other words, more work. So if this takes more work, that means this has got more energy in it at this point. So if we actually stop and we look at what we just identified, if we're talking about gravitational potential energy, so we're going to say, if we're talking about GPE, and let's actually identify this the proper way. Now let's go ahead and get rid of GPE, and let's just label it right. Let's call it E sub G. If we're talking about gravitational potential energy, what do we notice is involved in this? Well, we already said here that the higher up it is, the more energy it has, so the height has got to be something that's critical. So we know that the height is a factor in gravitational potential energy. And let's write it over here a little bit. Let's write it out. So height is a factor. Well, then if we look over here, we talk about what's down there. Well, we know that the bowling ball not just is bigger, but it has more mass. So that means mass is going to be another factor. So mass is a factor. But this isn't enough, because if I just have more mass and more height, that's not enough to talk about the gravitational potential energy that something has. We also have to take into account what's connecting these two. So what's actually connecting these is the fact that something's pulling on these at all times. Well, we know what's pulling: gravity. So that means gravity is going to be a factor too. Let's go with a gray. So that means we're going to have gravity in there. So that means all three of these things all come together to determine how much energy that an object has, how much gravitational potential energy an object has. So if we were to write the formula out, we'll have the gravitational potential energy of an object is equal to the mass times the gravity times height. We know that this is 9.8 meters per second squared, rounded up to 10. So this is just going to be the acceleration of gravity. We know that our energy, our potential energy, that's got to be in joules. And because that's in joules, we know what these two have to be in. We know that this has to be in kilograms, and that this has to be in meters. So this is height. Well, you can see that right there. So that's height, that's mass, that's gravity. So we have those three things. So what we have here is we have our formula. The potential energy of gravity is equal to mass times gravity times height. Now that we know the calculation for gravitational potential energy, we know that energy changes. We know that energy can change. We know that if we pull back a rubber band, if we let it go, it instantly turns into kinetic energy. We know that if we take a ball and we hold it up really high up in the air, that that ball is going to change its energy from being high up in the air to being energy of movement. So kinetic energy. We know that these energies can change back and forth. So let's take, once again, let's go to the dropped ball object. Oops. The dropped ball. And we have an object up a certain amount of height. We'll just call it h. If that ball is dropped, what do we know about the energies at these two positions? And we'll say this is right at the ground. Okay, so that's right before the ground, right before it hits the ground. Well, we know that up here, before it starts moving, we know that this is going to be a lot of gravitational potential energy. I don't know why I wrote an 8 there. Let's fix that. So gravitational potential energy. But we said we don't use that anymore, so let's call it what it is, or let's label it properly, EG. So we know this is all gravitational potential energy. As it falls, it's going to pick up speed. It's going to pick up movement. Well, if it's picking up movement, it's going to be picking up kinetic energy. Well, there's nothing here to add energy to it, so that means it had to be taking its energy from gravitational. So that means when it gets all the way to the bottom, there's going to be no gravitational potential energy left, but there's going to be all kinetic energy. Now, mind you, this is before it hits the ground. Keep that in mind. So that means all the energy down here is going to be kinetic. That means all of the energy is transformed from potential energy to kinetic energy. It's still a horrible K there. Let's see if I can fix that. That's better. So to kinetic energy. So that leads us to the next thing. If I know that the energy can transform back and forth, I have a statement that I want to make. So here's the statement. The statement is that the energy of the elastic potential energy or the gravitational potential energy is equal to the kinetic energy when, and that's the big thing, when the energy is completely stored or the object is moving at peak. By peak, I mean as fast as it possibly can. So is this statement true? Is the energy possible when it's completely stored, the energy stored for elastic energy or gravitational potential energy, is that going to be equal to the amount of kinetic energy of an object moving at its peak? And the answer to that is going to be yes. Because in this situation, is there anything to take energy away from this situation? There isn't. There's nothing pulling energy away. There's no, we'll say there's no air resistance, or air resistance is negligible. There's no impact here, so we don't have any thermal. There's no sound here, despite what you hear in cartoons. There's no whistling sound as an object falls. So all of the all of the elastic energy and gravitational energy will be transformed into kinetic energy. So what that means, now mind you, this is assuming no work or thermal energy. So that's assuming this is going to fall and we're not going to have any air resistance, and this ball, the change of this energy isn't going to be used to move something else, or that no other energy is added to this, like someone pushing down on the ball or something along those lines. So we know that all this energy is going to be transformed. So what that tells us then is that all this energy is going to turn to kinetic, which means we can start looking at the kinetic energy. So let's go ahead and let's look at kinetic energy. So what do we know about kinetic energy? What do we know about it? Well, what does it need? What does kinetic energy need? Well, we know this is the energy of movement, so it's got to have movement. So we know that an object is moving when it comes to kinetic energy. Well, the more it moves, the more kinetic energy it has, right? So how do we measure that? Well, how do we measure movement? Do we measure it in distance? Can't. Because I can have a ball that I pick that ball up and I carry it and I drop it off right here. Well, it's moved a distance, but if I'm looking at the ball at this point or at this point, it's not moving. Therefore, it has no kinetic energy. So we can't use distance. That ain't going to work. Well, what's a way of measuring the movement of something? Speed. Speed is the easiest way to measure something. So when we measure movement, we're actually going to be measuring velocity. Let's fix that letter T there. So velocity. So we have that. So let's go ahead and let's start our equation. We know that kinetic energy is equal to, and we know that, let's add a new color, or let's put a color in here. Let's call velocity blue here, VLOCITY. So we've got velocity. Well, what else is a factor there? Well, let's go back to the bowling ball and the regular ball. So there's our bowling ball, albeit poorly drawn. And there's our regular ball. Now, if both of these were falling, and that downwards, we'll ignore gravitational GPE for this point, or EG. If you were to have to stand underneath one and catch it, let's just start over. That's better. And we'll give him a small head. Tiny guy. Really long legs now. So, if you had to stand and catch one of these two, which one would you rather catch? Would you rather catch the big bowling ball or the small tennis ball? Well, logic would suggest you'd want to catch the large one, right? Yeah, because it's bigger, right? No. You don't want to catch that. That's going to be a lot heavier. It's going to be a lot harder to catch. That's going to hit you with a lot more force. You're going to want to catch this one. Because this one, because it has so much more energy, is going to be much harder to catch. Well, what makes these two different? You don't want to say size, because I can have a steel ball bearing and a big beach ball, and that steel ball bearing is going to weigh more. So what it's going to be is it's going to be the mass. Okay? So that means the mass is going to be a factor too. So that means we've got mass in this equation. So we've got mass times velocity. Well, if we go back a couple of experiments where we actually go, when we calculated what's going on here, when we're looking at energy, we know that when we take something like this, we have force on the side and distance, or yeah, change of position here. We know that the area underneath is the actual energy for this particular setup. Well, with kinetic energy, it's pretty much the same thing. Once again, it's the area under the triangle that we're looking for, just with different variables on the side. And so if we're looking at the area of a triangle, we know that it's 1/2 base times height, which means we've got to put that half in there, because here's our base, here's our height, because kinetic energy relies on mass and velocity. So we're going to add the 1/2. So it's 1/2 mass times velocity. But if we look at our recent lab, our recent experiment, in which we saw the effect of velocity by adding more and more energy to it, we noticed that if velocity was on the x-axis and the energy was on the y-axis, we noticed that it increased dramatically, which means it increased exponentially, which means to linearize this, because it was a parabolic shape, we would have to square velocity. So what that means then is we have to square it here. And what this gives us is this gives us our kinetic energy formula. Our kinetic energy formula is Ke is equal to 1/2 mv squared, where velocity is in meters per second, mass once again is in kilograms, and kinetic energy is in joules. So that's our other equation we have from this whole thing. And that's not a 1. Let's go ahead and, we can erase that. You know what don't want to confuse anybody there. So there we go. So just to sum up, we know that we found that the energy is going to change back and forth. And sorry, my voice is going there. The energy can change back and forth from potential to kinetic. We can lose some in thermal, but now we've identified the equations that we can use if we want to figure out how much kinetic energy something has, or potentially how fast it's going. We can also figure out how much gravitational potential energy something has, and using those two we can figure out how fast something's going based on its height or something along those lines. Once again, I want to thank you for watching this video. If you have any questions, feel free to leave them in the comments below, or if you have any suggestions, I like having those put in the comments below as well, so that way I know what you guys would like me to work on next. Thanks again for watching.